Let your body sink into the quiet. Whatever the day held, you can set it down now. Come with me, gently, into the slow, quiet story of how moons are born. If these help you sleep, subscribe. I post a new one every night. In the early dark of the solar system, before the Earth had found its final shape, a world held still. It was not a large world. Across its diameter, the distance was something close to the width of Mars, roughly 4,000 miles of rock and silicate and heat, gathered slowly over millions of years from the dust that circled the young sun. It held its position at one of the quiet gravitational pockets along Earth's own orbit, a place where the pull of the sun and the pull of the forming Earth balanced each other into something like equilibrium. There were two such pockets ahead of Earth and behind it along the curve of the orbit, places where a third body could rest without being drawn toward either of the two larger masses, suspended in the slow geometry of the early solar system, as if placed there deliberately and left. This world rested in one of them. It had been there for a very long time. The light that reached it was young light, brighter and harsher than what reaches Earth today, because the sun in those years was still contracting and changing, still finding its long, stable warmth. But at the distance where this world orbited, the light was already faint enough that the sky beyond it would have been almost entirely dark. The solar system had not yet swept its orbits clean. Between the planets, the space was thick with drifting rubble, small bodies, tumbling slowly, catching the light on one face and turning the other into blackness. The world that would later be called Theia moved through this crowded dark, tracing its orbit, holding its balance, unaware in the way that all worlds are unaware of what gravity was quietly preparing. For millions of years, that balance held. The early solar system was not a stable place. Gravity is patient, and it works on everything at once. The other planets, the ones that were forming, migrating, shifting their own orbits through the drag of the surrounding gas disk, were moving in ways that sent ripples through the gravitational field that held Theia in its quiet pocket. Small perturbations at first, barely measurable, the kind of shift that over 10 million years amounts to almost nothing, and over 100 million years amounts to everything. Thesa's orbit began to change, not suddenly, not catastrophically at first, just a slow incremental departure from the path it had traced for so long, a drift outward and then inward, the delicate balance of its gravitational shelter beginning, almost imperceptibly, to fail. The drift became a lean, the lean became a curve, and the curve, after a span of time almost impossible to feel the weight of, became a trajectory toward the growing world that had once been its gravitational partner from a safe distance. What followed was not an explosion in the ordinary sense. The word collision suggests a sudden, sharp event, two objects meeting in an instant, a crack, a flash, and then the aftermath. But the impact that formed the moon was something slower in its nature, something more like a process than a moment, even if by the standard of geological time, it was very nearly instantaneous. The Waya did not strike the Earth head-on. The simulations that reconstruct this event, careful numerical models that track the motion of millions of particles under gravitational and pressure forces, consistently show that the geometry of the approach was oblique, an angled path, a glancing contact, something between 30 and 45 degrees from the vertical, so that the two worlds did not simply stop each other, but instead skidded together, each dragging the other into a shared rotation, their outer layers peeling away into space while their cores bent toward each other and eventually merged. At the moment of contact, the sky would have vanished. The face of the Earth that met Thea's approach would have seen the other world arrive as a shape growing larger on the horizon, and then larger still, and then a wall, and then everything at once. The temperatures at the contact interface were far beyond what any rock can remain solid at, far beyond what air could survive without becoming plasma. Silicate rock, the stuff of which both worlds were built, does not simply melt at those temperatures. It vaporizes. It becomes a gas. And gas, released at the energy scales of a planetary collision, expands outward in all directions faster than any sound could follow. The two worlds were not destroyed in a single sharp moment. They were liquefied, then vaporized, then flung outward along the curve of the impact geometry, a stream of superheated silicate vapor and half-molten droplets spreading outward from the impact site in an enormous arc that curved up and out into the space above the young Earth. The contact lasted, in its most violent phase, only a few tens of minutes, but those minutes reshaped everything. The debris did not escape. The Earth's gravity, now augmented by the mass of Thea's core sinking into its own, was enough to hold most of what had been thrown outward within a shell of space several Earth radii wide. What expanded outward into that space was not a uniform cloud, but a disk, a broad, flattened structure of silicate vapor and condensing droplets, slowly rotating around the young Earth, glowing with the heat of its own creation. From within the debris field, if any surface had existed to stand on, the sky would have been a deep and luminous orange, shading to white where the densest clumps of vapor were still incandescent, shading to dark at the edges where the thinning material had already begun to cool. The disk extended outward in all directions from the Earth's equatorial plane, its inner edge merging with the Earth's upper atmosphere and its outer edge dissolving into the dark of space, a glowing ring of what had once been two worlds, now mixed and suspended, and slowly, over thousands of years, beginning to change. Researchers who model this early post-impact phase have given a name to one possible form the structure took in those first hours and days. The term is synestia, coined by Simon Locke and Sarah Stewart to describe a particular configuration in which the energy of the impact is high enough to vaporize such a large fraction of the combined mass that the result is not a planet surrounded by a disk, but something more continuous, a single, rapidly rotating body of vaporized rock in which the inner part spins as a planet would, and the outer part spreads into a torus, a thick ring blurring inward into the interior and outward into space, the boundary between planet and disk, not a sharp line, but a gradual gradient of density and temperature, a donut of vaporized rock, thousands of kilometers across, glowing faintly at its outer edges, churning slowly in the dark. The synestia, if that is what the post-impact Earth became, did not last long in geological terms. As it radiated heat into space, it cooled. The vapor at the outer edges condensed first, tiny silicate droplets forming where the temperature had fallen just low enough to allow liquid rock to exist, each droplet a fraction of a millimeter across, falling slowly inward under the pull of the Earth's gravity, joining other droplets, growing as it fell. The inner parts cooled more slowly, holding their heat longer, the whole structure gradually contracting and differentiating as the vapor became liquid, and the liquid became solid, and the solid began to feel the gravity of its neighbors and gather. The Earth re-emerged from the shrinking synestia as a recognizable planet within the outer disk's lifetime, and the outer disk, now separated from the contracting Earth, hung in its orbit with a new independence, no longer part of the planet that had formed it. Within that disk, something was beginning. The disk in those early years was not a quiet place. It was dense enough that collisions between particles were frequent, not the high-velocity shattering impacts that happen in asteroid belts, but softer, more intimate contacts. The kind of collision where two droplets moving at slightly different speeds meet, and because they are still partly molten or coated in a thin film of cooling silicate, stick. Sticking is the beginning of growth. Two droplets become one. One droplet, slightly heavier than the ones around it, falls through the disk along a slightly different arc and sweeps up others as it goes. The particle that was once a sand grain becomes, over thousands of years, something the size of a pebble, and then a stone, and then a boulder, and then something that has enough mass to pull other material toward itself with its own gravity, its own local field of attraction, no longer just a passive drifter, but an active gatherer, a center of slow accumulation. This process, this gradual, unhurried assembly of small into large, is called accretion. It is not fast by any measure human experience provides. The formation of the moon from the post-impact debris disk is thought to have taken somewhere between 1,000 and 100,000 years from the time of the impact to the time when the moon became a recognizable body, a sphere with a surface that curved away from you in all directions, the world. By the scale of stellar or even planetary evolution, this is an eye blink. 100,000 years is the kind of time that a slow geological process, the widening of a rift valley, the accumulation of a sediment layer, might take to produce a visible result. It is almost nothing against the 4.5 billion years that the solar system has since endured, and yet within it, a world was made. The angular momentum transferred into the Earth-Moon system by the oblique geometry of the impact shaped everything about how this accretion occurred. Because the debris disk was rotating in the same direction as the now spinning Earth, and because the angular momentum of the system was high, the debris did not simply fall back toward Earth and be absorbed. The rotation kept it aloft. The outer parts of the disk moved fast enough to stay in orbit, and it was from those outer parts where the density of material was high enough to sustain accretion, but the inward pull of Earth's gravity was balanced by the speed of the orbiting material, that the moon's earliest mass began to accumulate. And the numerical simulations that produce this picture, the smoothed particle hydrodynamics models that track millions of virtual rock droplets through gravitational and pressure forces, show consistently that only the oblique impact geometry reproduces both the mass of the moon and the angular momentum of the present Earth-Moon system. A head-on impact produces a different result entirely. The angle was not incidental, it was the thing that made the moon possible. Through the first few centuries after the impact, the growing body at the outer edge of the debris disk was already distinguishable from the surrounding material. It was larger, it was more massive. Its gravity was reaching farther into the disk, pulling in material that would otherwise have continued to orbit the Earth independently, sweeping lanes clear ahead of it and behind it, growing faster as it grew, because each addition of mass made its gravitational reach slightly wider. A body that grows faster than its neighbors tends to continue growing faster. In the disk, over the course of thousands of years, this one accumulating mass became dominant, clearing the disk around it, gathering the last of the loose debris into its surface as a series of low-velocity impacts that added heat as well as mass, keeping the outer layers of the growing moon molten long after the first solid surface might otherwise have formed. The surface of the moon in those early years was a magma ocean, not a metaphor, but a literal global sea of liquid silicate rock, dark and viscous on the surface where the heat was escaping fastest, incandescent at depth where the pressure kept the melt hotter still. The moon glowed. From the Earth's surface, if any surface had yet formed there, the moon would have hung in the sky as an enormous, faintly luminous disk, not reflecting sunlight as it does today, but generating its own dim light from the heat stored within its newly accreted body. The two worlds in those early years faced each other across a distance much smaller than today's. The moon had not yet begun the slow outward recession that billions of years of tidal interaction would produce. It was close, perhaps 15 or 20 times the Earth's own radius compared to the 60 Earth radii of its current orbit. The tides it raised on the young Earth would have been immense. The tides the Earth raised on it would have been greater still. This is the world that formed in the first 100,000 years after the collision, a sphere of molten rock, roughly a quarter the diameter of Earth, orbiting at a distance that today would place it clearly visible during the day, its surface slowly losing heat to the dark of space, its interior still churning with the memory of the accretion that made it. It was not yet the moon, as anyone now knows it. Its surface was not yet solid. Its craters had not yet been carved. Its dark maria and pale highlands were still undifferentiated within the global melt. But the shape was there. The gravity was there. The orbit was there. The mass had gathered from dust and vapor and colliding droplets into something coherent, something that bent space in its immediate neighborhood and held its own form against the tidal pull of the planet it had been born to circle. The disk from which it had grown was already thinning. The moon had swept up most of what there was. Small amounts of material still drifted in the inner disk, some of it falling back toward the Earth, some of it being captured by the moon's gravity and adding to its outer layers, some of it slowly dispersing into independent orbits that would drift away over long timescales. But the main work of accretion was done. The disk was becoming transparent. The debris that had glowed orange and white in the aftermath of the impact had condensed and coalesced and gathered into two bodies, the regrowing Earth below and the new moon above, and the space between them was quieter now than it had been in any moment since Theia first began its drift from the Lagrange point where it had waited for so long. The early solar system was still not a calm place. Beyond the forming moon, the space was still populated with the remnants of the debris disk and the broader cloud of planetesimals that had not yet been swept into any planet. Some of these would strike the moon in the ages to come, carving the great basins that are still visible today, flooding them later with dark volcanic rock. But those events were millions and hundreds of millions of years in the future. In the immediate aftermath of accretion, the moon was simply cooling, simply rounding, simply becoming. There is something in the quality of that becoming that the mind reaches for without being able to fully grasp. The process that assembled the moon was not designed. No force within it understood what it was making. Gravity reached, and the particles fell toward each other, and the heat of their falling bound them together, and the accumulation of 1 trillion such falls over thousands of years produced a sphere. The sphere cooled, its surface hardened, its interior differentiated, and one day, not any single day, but a long, slow day, spread across centuries, the moon was finished assembling, and it hung in the sky of the young Earth, solid enough that if you could have walked on it, you would have felt the ground hold you, and close enough that it filled a much larger portion of the sky than it does now. The collision that made it was, in the language of ordinary experience, a catastrophe of the highest order. Two worlds destroyed, two differentiated bodies melted together and spun out into space. The heat of it would have sterilized any surface within the solar system's inner region. The light of it would have outshone the sun briefly. And from that catastrophe, from that long grazing contact between one world and another, from that slow disaster of heat and angular momentum and vaporized rock. The thing that rose was the moon. Destruction and creation do not oppose each other in the deep history of the solar system. They are the same motion seen from different distances. The same oblique contact that tore two worlds apart transferred into the system the angular momentum that would eventually slow the Earth's early rotation and recede the moon to its current distance and lock the moon's face permanently toward the planet that made it. The same debris disk that was the graveyard of two planetary bodies was the nursery of one more. The impact that from close up would have seemed like the end of everything was, from the distance of 4.5 billion years, simply one step in a longer accumulation, a brief and violent turn in the patient, unhurried work of gravity, gathering matter into worlds. The moon that grew from the cooling debris that assembled itself over millennia from the shattered remains of the impact was already carrying within its composition the record of what had made it. The silicate that formed its mantle had been part of two different worlds before it became part of one. The heat stored in its magma ocean was the converted kinetic energy of all those falling droplets, all those gentle collisions between cooling particles in the dark of the disk, and the orbit it occupied, circling the Earth at an angle that reflected the direction of the impact, moving in the direction of the Earth's rotation, but at a slight tilt to the equatorial plane, described in its geometry, the angle at which Theia had arrived. Everything the moon is, it is because of how it was made. Every feature of it, the mass, the orbit, the asymmetry between the two hemispheres, the depth of the magma ocean, and the thickness of the crust that eventually formed above it, traces back in some way to that single event, that one oblique contact between a Mars-sized world and the proto-Earth, lasting a few hours in its most violent phase and a few 100,000 years in its aftermath. And yet, from the scale of the present, looking back across the immensity of time that separates now from then, even that long aftermath seems brief. The solar system had been forming for tens of millions of years before the impact. It has been in something like its current configuration for 4 billion years since. The moon's accretion, spanning as much as 100,000 years, is a thin line on that timeline, barely visible, an almost instantaneous event that left a world behind. The debris disk thinned and cleared. The last loose fragments either fell to the moon, fell to the Earth, or drifted away into trajectories that would take them far from where they had been born. The space between the Earth and the moon grew quieter. The moon's surface, still glowing faintly, was already beginning the long process of cooling that would eventually produce the solid anorthosite highlands visible today. The magma ocean was beginning its fractional crystallization, denser minerals sinking slowly toward the interior, lighter ones rising toward the surface, separating the moon's composition into layers that would endure for billions of years. But that differentiation was still in its early stages. The moon was still new. Its surface was still largely molten. Its orbit was still changing, still adjusting under the mutual tidal forces of the Earth-Moon pair. And the Earth itself, its upper layers still disrupted by the impact and the loss of so much material to the disk, was also reorganizing, its iron core deepening, its mantle convecting, its surface somewhere between ocean and magma, not yet the world it would become. Two worlds, damaged and reformed, orbiting each other in the dark. The sun shone on them both. The early solar system continued its slow settling. And somewhere in the cooling magma of the new moon, silicate crystals were beginning to form for the first time, tiny ordered structures, precipitating out of the melt as the temperature fell below the threshold at which rock could remain liquid. Each crystal was a kind of record, a physical memory of the temperature and pressure at the moment of its formation. The crystals grew slowly, and the magma ocean above them cooled slowly, and the moon hardened slowly, from the inside out and from the outside in, until one day, spread across millions of years of cooling, there was more solid than melt, and the moon's surface held its shape against the slow heat rising from below, a world rather than a cloud of rock, a sphere rather than a disk, something with a horizon and a gravity that held itself in place, and a face that the earth had already begun to pull toward it in the slow, patient process of tidal locking that would take hundreds of millions more years to complete. The debris that had once been two worlds had become one more, not lost, not destroyed in any final sense, changed in form and in arrangement, recombined by heat and gravity into something that had not existed before. Vaya drifted from its quiet pocket at the Lagrange point and began its long, slow arc toward the earth. The moon rose from the settling disk and took its place in the sky, and the sky has held it ever since, and the light it reflects on sleeping worlds below it is old light, grown only a little older, carrying nothing of the violence that was there at the beginning, only the quiet, familiar glow of a world that has long since settled into what it is, cooling still, receding still, turning its one face toward the earth in the slow and patient way that gravity arranges things when given enough time. The impact was over. The disk was gone. The moon was there, and in the dark above the young earth, still warm from everything it had just endured, it moved in its orbit through the silence, the first revolution of many, too many to count, each one carrying it a little farther from where it was made, each one a small step in the immense and quiet recession that has brought it to the distance it occupies now, this night, above the sleeping world below. At the far edge of the solar system, where the sun has shrunk to a point of cold white light, no brighter than the brightest star in a city sky, a small world moves through the dark at a walking pace. Not slowly by the standards of the deep outer solar system, where everything drifts, but slowly in the way that a thing can seem almost still if watched for only a moment. Its surface is pale. Water, ice, and frozen nitrogen coat the rock beneath in layers built up over billions of years of cold accumulation, and in the faint sunlight at that distance, the surface holds a faint bluish gleam, the color of old snow pressed deep in a glacier. No wind touches it, no weather moves across it. The only sound, if sound could travel there, would be the complete absence of everything, a silence so total it has a texture. This is the outer solar system, past the great gas planets, past the point where the solar disk once ended and open space began. The objects out here are ancient. They formed in the cold margins of the early solar nebula, accreted from ice and rock and carbon compounds, and then were scattered outward by the gravitational jostling of the giant planets forming inside them. Some were flung clear of the solar system entirely. Others settled into long, slow orbits in this distant region, where they have circled the sun so many times that the number is difficult to hold. They are remnants, leftovers, the material that was never gathered into something larger. The small world carries no name yet, in the sense that matters here. It is one of many, though larger than most, a few hundred miles across, its surface a patchwork of nitrogen ice and darker organic compounds laid down grain by grain over the eons, its interior a compressed mixture of rock and water ice that has never melted, never been touched by internal heat. It moves in company with another world almost exactly its size, and the two of them orbit each other slowly, a gravitational pair, their shared center of mass tracing a wide arc around the sun. Binary worlds like these are not rare out here. Two objects that formed close together or that drifted together early and found each other's gravity enough to hold will orbit in this kind of slow embrace for billions of years, companionable in a way that has nothing to do with life or awareness. They simply turn, each around the other, as naturally as anything in the universe turns around anything else. The sunlight that reaches them is faint enough that it takes several seconds to cross the distance from one face of the pair to the other at that range. From where they travel, the sun is a point, the planets are invisible. The inner solar system, with its warmth and its complex chemistry and its slowly evolving geology, is as remote from this place as a fire seen from a great mountain on a clear night, present, faintly suggested, and entirely untouchable. They have been here a very long time, circling this way. The inner solar system has changed almost beyond recognition since these two worlds settled into their outer orbit. Planets have migrated, bombardment phases have come and gone, continents have shifted on the surfaces of worlds they will never approach. But out here, in the cold beyond the reach of any of that, the two worlds have simply continued their slow, mutual turning, patient in the way that only things without patience can be. Patient because there is no other option, because orbital mechanics does not offer one. What changes, when it changes, does not announce itself. The change is a slow accumulation of tiny perturbations, gravitational nudges from the giant planets millions of miles inward, influences so faint that measuring them directly would require instruments that do not exist. Over long spans of time, the combined effect of these gentle tugs alters the pair's orbit in increments too small to observe in any single pass, until eventually the path that was stable for so long is stable no longer. The orbit begins, almost imperceptibly, to change. The pair drifts, by increments, onto a new trajectory, one that carries them slowly, across millions of years, not deeper into the outer dark, but inward, toward the warmer regions, toward the giant planets, toward Neptune. Neptune is enormous. At this distance from the sun, it is the dominant gravitational presence in the sky, a pale blue disk 4 times the width of Earth, visible from distances where no inner planet would show a disk at all. Its gravity reaches outward in a field that cannot be seen, but can be felt, not as a physical sensation, but as a curvature in the invisible geometry of space around it, a shape that everything moving nearby must take into account. The two small icy worlds cross into Neptune's outer gravitational influence gradually, their speed increasing almost too slowly to measure as the planet's mass draws them in. They are still bound to each other, still circling their shared center of mass, still a pair, but the geometry of their close approach to Neptune will not be the same for both of them. One will pass closer to the planet on its first swing through the Hill sphere, the region of space where Neptune's gravity dominates over the sun's. The other will pass farther out, and this difference, small as it seems, is everything. A Hill sphere has no boundary that can be seen. It is not a wall or a line. It is simply the zone within which Neptune's gravity can bend an incoming trajectory enough to capture it, provided that energy is taken away from the object in question, because without losing energy, any object on a hyperbolic path will follow its curve back out again into the dark, just as it came. The mathematics of two-body orbital mechanics are exact on this point. A world approaching on an open, unbound path will remain on an open, unbound path unless something takes energy away. In most cases, nothing does. Most encounters end the same way they began, with one object curving away into open space, unaffected. But binary pairs change this. When two objects orbit each other, they share a pool of orbital energy, the energy of their mutual motion around each other, their shared angular momentum, their gravitational binding. When a giant planet disrupts that pair, the energy in the system can be redistributed between the two members. One member, in the right geometry, can give up enough orbital energy to the other that it slips onto a bound orbit around the planet. The other, taking on that energy, is flung outward, accelerated onto a new trajectory that carries it away and does not return. The exchange happens fast by planetary standards, in a matter of hours or days of close passage, and the result is permanent. One world is captured, one world is gone. The pair, which has been a pair for billions of years, is divided in a single close approach. The smaller of the two swings through Neptune's hill sphere on a trajectory that gives it back to the dark. It departs at a new angle, with new speed, on a path that will carry it into the inner solar system or out of it entirely. The record does not preserve which. It leaves no trace in what remains. Its companion, the larger world, the one that will later be called Triton, curves through a different arc and does not escape. The initial orbit is not a circle. It is a vast, stretched ellipse, wildly eccentric, carrying Triton from a periapsis close to Neptune out to an apoapsis so distant that it grazes the cold region from which it came. The period of this orbit is long, perhaps decades per circuit in these early captured years. At its closest approach, Triton sweeps in fast, and the gravitational field around it grows strong and complex. At its farthest, it moves slowly through near empty space, a pale dot barely distinguishable from the background of the outer dark. It is in these early years a world in transition, neither fully free nor fully settled, held but not yet comfortable, caught but not yet still. The other thing that happens at each close passage is less visible but more consequential. Tidal forces are the result of gravity falling off with distance, the near side of a body feeling a stronger pull than the far side, and the differential stretching the body slightly in the direction of the source. For small objects at large distances, this stretching is negligible. For a world of Triton's size, swinging close to a planet as massive as Neptune on a highly eccentric orbit, the stretching at each periapsis passage is substantial. The interior of Triton, which has been cold and rigid and undisturbed for its entire history, begins to flex. Rock and ice that has been still for billions of years is pushed and pulled on a rhythmic schedule, stretched inward as the world swings close and relaxing as it recedes. This flexing is not free. It costs energy. The energy comes from the orbital motion itself. Each periapsis passage extracts a small amount of kinetic energy from Triton's orbit and converts it to heat inside its body. The orbit, losing energy, shrinks. The apoapsis, that far distant point, draws in a little closer. The eccentricity, the degree to which the orbit is stretched rather than round, decreases slowly by an amount too small to notice in any single orbit, then too small to notice in 100, then in 10,000. But over millions of years, the accumulation of these tiny extractions changes the orbit's shape. A world that once swung between close and far settles, gradually, onto a path that is less stretched, less extreme, the near and far points drawing together toward a common distance. This process is called tidal circularization. The word circularization understates the time it takes, The best estimates run from 100 million years to 1 billion years for Triton's orbit to reach its present form. 100 million years is a span in which continents have time to travel thousands of miles, in which ice ages come and go dozens of times, in which evolution, given the right conditions, can transform one body plan into another almost unrecognizable one. And yet, through all of that time, on a world with no life, and no weather, and no geology driven by plate movement, the only thing happening is the slow, relentless extraction of orbital kinetic energy by tidal flexing, orbit by orbit, close approach by close approach, the shape of the path growing less elongated with each circuit. The heat generated by this process does not simply disappear. It goes into Triton's interior, a world that spent its entire previous existence frozen solid, too far from the sun for any internal heat to be generated by radioactive decay in significant amounts, now has a new heat source, the tidal flexing of its own rock and ice. The interior warms. Some of the ice that formed billions of years ago in the cold of the outer solar system begins to soften, to become plastic, to allow slow internal movement. There may be for a time a liquid water ocean somewhere beneath the surface, a possibility that leaves no definitive trace but is consistent with the physical conditions. The surface, always cold from the outside, radiates heat away to space from above, even as the interior warms from below. Triton is, for this long period, a world between states, too cold to be geologically active in the way the inner planets are, but no longer entirely frozen and inert. The orbit, meanwhile, keeps shrinking. The eccentricity keeps declining. The path keeps approaching a circle. At some point during this long process, and the exact timing is uncertain enough that no specific moment can be named with confidence, Triton's orbit also becomes retrograde. This word carries the full weight of what Triton is. Neptune rotates in one direction, and nearly everything that formed in Neptune's circumplanetary disk orbits in that same direction, as naturally as planets orbit the sun in the direction the original nebula rotated. A moon that orbits in the opposite direction against Neptune's rotation was not born there. It was not assembled from the same disk that assembled the planet beneath it. It came from somewhere else, arrived on a path the disk never traced, and was caught. Triton orbits today at an angle that takes it backward across Neptune's sky, if Neptune had a sky worth standing under. From any reference frame aligned with Neptune's rotation, Triton moves the wrong way. This retrograde motion is not an anomaly in the sense of a puzzle with no solution. It is, precisely, the fingerprint of capture. It cannot be explained by any model of in-place formation. No process that builds moons from a circumplanetary disk produces a moon in retrograde orbit. The orbit is the record of the event, more durable than any other trace, still present billions of years after the binary disruption, and the long tidal settling are finished. The surface of Triton, when it finally stabilizes into its nearly circular retrograde orbit, is not quite the same surface that emerged from the outer solar system. Tidal heating has reworked some of it. The interior has settled into whatever configuration it will hold from here on, and then will aid over the remaining span of time until the present. The surface begins to accumulate what it accumulates today, a mixture of nitrogen ice and methane and carbon monoxide, deposited from a thin atmosphere so tenuous that it barely qualifies as one, at temperatures that can fall low enough that the thermal energy of the molecules is almost entirely gone, temperatures that approach within a few dozen degrees of absolute zero. There are geysers on Triton. They rise from the surface in dark plumes, visible against the pale pinkish white of the nitrogen ice plain, columns of gas, and dark dust carrying material from just below the surface upward into the near vacuum overhead. They are driven not by the kind of volcanism that drives geysers on Earth, not by liquid water under pressure, not by magma heating a water reservoir, but by solar radiation, even the faint, distant radiation that reaches Triton, penetrating a transparent layer of nitrogen ice and warming a darker layer beneath it, converting the frozen nitrogen to gas in a cavity below the surface until the pressure is enough to break through. The plumes rise a few miles into the sky, then drift downwind and fall as a dark coating on the ice, fanning out in streaks that can be traced across the surface. These plumes are the most visible surface activity on Triton, but they are not the residue of the capture. They are a surface phenomenon driven by the thin present of sunlight. The capture's legacy is deeper. It is in the slight warmth of an interior that might, in the absence of tidal heating, have been entirely cold. It is in the retrograde orbital motion. It is in the very fact that Triton is here at all, orbiting a planet it was not born near, in a direction that runs against the motion of everything that formed beside that planet. Some of the inner moons of Neptune, small, irregular, dark, may be fragments of larger moons that were disrupted when Triton first arrived, and its highly eccentric orbit cut through whatever system of original satellites Neptune had assembled. The violence of the capture, even without any direct collision, was enough to reshape the space around Neptune entirely. The original moons, if they existed, were gravitationally scattered, some to new orbits, some away entirely. What survived is a system rebuilt around the intruder, reorganized by the same event that ended the binary pair and installed Triton in its place. The long, slow settling after that reorganization is itself a kind of peace. Not a peace chosen or desired. There is no choosing here, no desiring, but the peace of orbital mechanics reaching a stable configuration, of energy dissipation completing its work, of eccentricity approaching zero. What was turbulent becomes, over enough time, smooth. What was eccentric becomes circular. What was new and disruptive becomes, over 1 billion years, the permanent familiar arrangement of a world in its finished orbit. Triton today does not look like a world that has been through anything unusual from the outside. It is a sphere. It has a surface. It orbits its planet at a steady distance, completing each circuit in a rhythm that does not change, year after year in the modern solar system. The retrograde motion is visible in the data, in the orbital elements, in the direction of the planet's shadow as it crosses the surface during the rare alignments that produce occultations. But to a casual view, it is simply another moon. Closer in, the surface tells a quieter version of the story. The nitrogen ice plains are younger, geologically, than many lunar surfaces, because volatile compounds deposited from a thin atmosphere are constantly refreshed at Triton's temperatures, covering older features, resurfacing in slow increments. Beneath the smooth ice plains, there are regions of older terrain, more complex, rougher, whose origin is debated. The interior holds some warmth, more than the background temperature of the outer solar system would account for if the world had simply sat undisturbed in the cold. The heat is there. Its source is the tidal flexing of the capture era, the energy taken from an orbit now circular, deposited long ago and still slowly working its way outward. Neptune hangs overhead, or what would be overhead if a surface existed under Triton's sky that could have an observer. The planet is large from this distance, a soft blue disk, banded with faint clouds, its color the result of methane in its upper atmosphere, absorbing red light and leaving blue to scatter back into space. It is large enough to show detail, large enough to track clouds across its surface, over the course of a day. The relationship between the two worlds, the planet and its captured companion, is now as stable as any orbital relationship in the solar system. The orbit Triton follows will not change significantly for a very long time, though eventually, over billions of years in the future, tidal forces from Neptune will continue their slow work, and Triton will drift inward by increments until it crosses the threshold inside which a solid moon cannot hold together against Neptune's gravity. But that end is remote, and the present is quiet. Gravity does not reach and grab in any literal sense. It does not pursue or intend. The bending of space-time that draws one mass toward another has no awareness of what it does. But there is a kind of elegance in the mechanics of capture, not the elegance of intention, but the elegance of physics working out its consequences without remainder. Two worlds arrive, bound to each other. One leaves, one stays. The one that stays is reshaped by the very process of its capture, its interior warmed, its orbit smoothed, its surface eventually made host to the geysers that rise from it today. The end state is not what any incoming observer could have predicted from the approaching pair in the outer dark. It is what the mathematics produced, one slow orbital adjustment at a time until the dissipation ran down and the motion settled and the world found its place. Nothing that formed near Neptune found its place this way. The moons that assembled from Neptune's circumplanetary disk formed on circular prograde orbits, built from the same material that was already moving in the same direction as the disk. They did not need to be circularized. They did not generate internal heat by flexing. They arrived in their orbits without drama, accumulating quietly from the same rotating disk that was slowly building Neptune itself, and they have simply remained there, unremarkable in their origin, steady in their paths. Triton arrived differently. It carries the record of a different kind of arrival, the kind that begins not in a disk, but in the free cold of the outer solar system, in the gentle gravitational companionship of a binary pair, in a close approach that broke the pair apart and redirected one member into a new family, without asking and without ceremony. The breaking was fast, the settling was slow. The result is the world that sits in retrograde orbit around Neptune today. Nitrogen geysers rising from its pale surface, its interior slightly warmer than the surrounding dark, its orbital path running backward against the spin of everything that formed in place, and carrying in that path the permanent, quiet record of how it arrived. The pale surface reflects the faint sunlight that reaches this far. From the sun, at this distance, the light is ancient in the sense that it was already old before any eyes existed to see it. The nitrogen ice scatters it in all directions, sending a faint luminescence across the plain. The dark streaks from the geysers lie across the bright surface in long, narrow fans, marking where the plumes drifted and fell. Everything is still, except for the occasional new plume rising from the ice and the slow orbital motion continuing its circuit around the blue planet overhead. It has been still, in this way, for longer than there has been complex life on Earth. The orbit is circular now. The energy that was orbital kinetic energy is heat dispersed into Triton's interior over hundreds of millions of years of periapsis passages, each one taking a small fraction more and depositing it as warmth in the rock and ice below. That warmth has not entirely dissipated. Some of it is still there, slowly making its way outward through the layers, still shaping the internal conditions of a world that no longer flexes with each orbit because the orbit no longer varies. The heat is the last residue of the capture, a memory preserved in the temperature of a cold world's interior, still present, still slowly fading. the motion continues. The retrograde orbit carries Triton around Neptune in a path that runs against the planet's rotation, steady and unchanged, a path that will continue for a time longer than it is useful to count. The binary pair that once moved through the outer solar system together is a pair no longer. One is gone, lost to the dark, or scattered to a new path somewhere in the solar system's wide history. The other has been here long enough that the outer solar system it came from is simply where it is from, a provenance written in its orbit rather than in anything visible on its surface. It rests in its circular path the way something rests that has no capacity for rest or motion, that simply continues because the physics that governs it finds this configuration stable, finds it the arrangement that requires the least further change. The long settling is done. The wild ellipse of the early capture years is gone, replaced by a circle that varies by almost nothing from one orbit to the next. The world that once moved through the cold dark of the outer solar system in a binary embrace with another world now orbits alone, steady, in a direction no formed-in-place moon takes, around a blue planet it did not form beside, at peace in a way that only a great deal of time and a great deal of slow dissipation can produce. The plumes rise from the ice. The pale surface glows faintly in the distant sunlight. Neptune turns in the sky above, its clouds moving in slow bands, its blue deepening toward its poles. The orbit continues, retrograde and circular, as it will continue for a very long time, carrying the record of one of the outer solar system's older and stranger histories in the simple fact of its direction, steady and unhurried, and entirely, finally, still. From within the disk, the light does not come from any single direction. It filters through slowly, diffuse and golden, as though the air itself were made of something faintly warm. Dust drifts in long, slow currents that are almost invisible until a denser veil of particles catches the light at a particular angle and glows briefly, bronze and amber, before the current carries it away. The disk extends outward from the young planet at the center, a planet that is not yet finished, not yet solid all the way through, still warm from the long violence of its formation, and the material surrounding it rotates in the same direction the planet turns, all of it swept up into a single, vast, unhurried motion. This is a circumplanetary disk. This is where moons are born. The scale of it is easier to feel than to measure. From the outer edge, the planet at the center is a dim, massive presence, its upper atmosphere still hot enough to glow at certain depths, radiating a faint warmth that the dust particles at the disk's inner boundary can almost feel. Farther out, the disk cools degree by degree, the particles drifting through temperatures that drop slowly as the distance from the planet grows. At the inner regions, silica grains are the dominant solid material, tiny particles of rock, each one a fraction of a millimeter across, tumbling slowly in the gas. Farther out, where the temperature falls below the threshold at which water can remain vapor, ice begins to condense on the surface of those same grains, coating them in thin, brittle shells of frozen water. The boundary between these two zones is not a sharp line. It is a gradual transition, wide and slow, where particle after particle crosses the threshold and gains its coating of ice, and becomes, in that small way, something different from what it was before. Dust settles slowly toward the disk's midplane. The settling takes a long time. Each grain drifts downward through the gas, under a gravity so gentle that the motion is nearly imperceptible, slower than snow falling through deeply still air, slower even than that, a drift measured in years rather than minutes, in thousands of years across the full depth of the disk. But the disk has time. The disk has millions of years. and so the grains settle, and the midplane gradually thickens, and the density of solid material in that narrow central layer rises, grain by grain, over an immensity of quiet time. In the settling midplane, something begins to change. A region of the disk that was evenly spread, particles distributed uniformly through the gas, develops a slight imbalance, a faint and irregular thickening in one place. It is barely a difference at first. A few more grains per cubic kilometer, a density slightly above the surroundings. But solid particles and the gas they float in do not behave identically in the rotating disk. The gas is supported partly by its own pressure, which means it orbits the planet fractionally slower than a purely gravitational orbit would require. The solid grains, lacking that pressure support, feel a headwind from the gas. This headwind slows the grains and causes them to drift very slowly inward, spiraling gently toward the planet at the center over long periods of time. Where grains drift together, the local density rises. Where the density rises, the drag between the particles and the gas changes in a subtle but consequential way. The particles begin to concentrate further. The gas motion near the thickening responds to the particles respond to the gas. Each drives the other toward greater concentration. The clumping builds on itself without any single force directing it, without any mind choosing it, simply as the natural consequence of how gas and solid particles interact when they share a rotating disk. This is the streaming instability, a process in which material that was evenly spread begins, almost imperceptibly, to gather into something denser, and then into something denser still, and then into something dense enough that gravity among the particles themselves begins to matter. At some point in the clump's growth, its own gravity exceeds the forces that would disperse it. The particles in the densest regions begin to fall toward each other. The collapse is slow by any standard that a human lifetime could feel. It takes thousands of years, but by the scale of planetary formation, it is extraordinarily rapid. A cloud of drifting dust that had been spread across thousands of kilometers contracts into a body perhaps a few kilometers across, in what amounts, geologically, to an instant. This is the first planetesimal. Not yet a moon, not yet anything that a future observer would call a world, but a coherent body, something solid, something with a center. From that first solid body, the growth continues. Other clumps form nearby through the same process, each one collapsing from its own dense stream of particles, each one beginning its own slow gravitational conversation with everything around it. The largest bodies sweep up the smaller ones. Particles that are not swept up continue to drift in on the slow inward spiral, adding mass grain by grain over hundreds of thousands of years, then millions. The largest bodies grow. They round under their own gravity. They clear paths through the disk, and in the space around a young planet that would one day be called Jupiter, something like a family begins to take shape. 4 of these worlds will survive to become the Galilean moons. They do not know this yet. In the disk's early age, there are more, many more perhaps, an earlier generation of moons that grew in the same disk, following the same process, reaching sizes comparable to those that exist today. These earlier moons are lost. They do not survive. The gas of the disk exerts a drag on them, just as it does on the smallest particles, and the effect on a large body orbiting in a dense disk is a slow but inevitable inward drift. The moon loses angular momentum to the gas. Its orbit shrinks. Over hundreds of thousands of years, it spirals inward toward the planet it was born near, growing closer until the planet's upper atmosphere engulfs it and the moon dissolves. its material absorbed back into the body that gave the disk its shape. It leaves no monument. There is no record in the disk that it existed. The disk continues as though it was never there. This may have happened more than once. A generation forms, spirals in, and disappears. The disk is resupplied with fresh material from the outer solar disk, flowing in along the planet's gravitational reach, and the process begins again. What is important is not which specific moons form, but how many eventually survive, and the answer is determined by a simple balance. As long as the gas disk remains, it drives moons inward. When the gas disk disperses, blown away by the young sun's radiation over a period of millions of years, the inward spiral stops. The moons that exist at the moment of dispersal are the moons that will be there forever. The Galilean moons are the last generation. They formed late enough, or grew large enough, or occupied orbits far enough from the deepest region of the disk's drag that they endured while the gas thinned and the driving force faded. The disk cleared, the orbits held. These four worlds arranged themselves in the disk according to the temperature gradient that shaped their formation. Closest to Jupiter is the innermost, where the disk was warmest during formation and where no water ice could survive as a solid. Its material is almost entirely rock and silicate mineral. Its density is high, close to 3.5 grams per cubic centimeter, a density approaching that of some solid rocks on Earth. Its interior is dense and dry. The world closest to Jupiter formed from what the hot inner disk contained, and the hot inner disk contained mostly stone. Farther out, the next two worlds are denser than water ice, but less dense than pure rock, a mixture, their interiors layered with rock toward the center and ice toward the surface, the proportions reflecting the temperature at which their building material condensed. These middle worlds formed in the transition zone, where the disk was cool enough for ice to contribute meaningfully to the solid mass budget, but warm enough to favor rock over water in the innermost layers. They are differentiated, their denser rocks settled inward under the heat of formation, their lighter water ice settled above. The outermost of the four is the most distant and the coldest. Its average density is close to 1 8/10 grams per cubic centimeter, barely denser than water, lighter than any of the others. It is rich in ice throughout its bulk, a world whose building material came almost entirely from the cool outer reaches of the disk, where water was the most abundant solid substance available. It may not have differentiated fully during formation, its interior potentially a mixed mass of rock and ice that never separated cleanly into layers. It sits at the outer edge of the family, and it carries in its composition a record of how cold the disk was at the distance where it formed. These four worlds, arrayed outward from their planet in order of decreasing density, express something that the disk itself expressed, a temperature gradient, a slow cooling from the warm inner region to the cold outer edge, precisely parallel to the pattern that arranged the solar system's planets in the same order. Rocky worlds close to the sun, ice-rich bodies farther out, the frost lines setting the boundary between them. The disk that built the moons was a smaller version of the disk that built the planets. The moons remember the disk, the way a cross-section of wood remembers the seasons that grew it, each ring a different year, each layer a different temperature, the whole pattern preserved in the material itself long after the conditions that produced it have gone. The disk around the young Jupiter was not a fixed reservoir of material. This is a distinction that matters. The early picture of circumplanetary disk formation imagined a static mass of gas and dust surrounding the planet, material present from the beginning, slowly used up in the formation of moons, depleted over time. The model that emerged from careful calculation proposes something different. The disk is continuously resupplied. Material from the surrounding outer solar disk, still rich in gas and solid particles, flows inward along the planet's gravitational reach and supplements what is already there. The disk is not a closed system drawing down its stock. It is a slowly moving current, material arriving from the outside and drifting inward toward the planet, with the forming moons sweeping up what they can from the stream as it passes. This distinction resolves a puzzle that a static disk model cannot easily explain. The mass of all 4 Galilean moons combined is a very small fraction of Jupiter's mass, roughly 1/10,000th. If the disk had been much more massive, it would have driven the moons inward too rapidly through gas drag before the disk dispersed. If it had been too sparse, there would not have been enough material to grow the moons to their observed sizes. The continuously resupplied, or gas-starved, disk threads this constraint naturally. Material flows through the disk rather than accumulating in it, keeping the disk mass low at any given moment while still delivering enough total material over the full formation period to build a family of large moons. The disk is like a slow river more than a still lake, carrying its load through, not holding it. Saturn's large moon formed in the same broad way, a circumplanetary disk fed from the outer solar disk, solid particles drifting and clumping and growing under gravity, a world that assembled itself from what the disk contained at the distance where it formed. Its bulk is mostly water, ice, and organic-rich compounds, the composition consistent with formation in the cold outer reaches of Saturn's circumplanetary disk, where temperature was low and ice was abundant. It is large, the largest moon in the solar system by some measures, a world with a diameter wider than the planet Mercury, and it became something so complex that even its thick atmosphere, rich in nitrogen and shrouded in orange haze, is still the subject of ongoing investigation. Where the nitrogen came from, and how it came to dominate a moon of primarily icy composition, is a question that the disk alone does not fully answer. Some volatile inventory carried in from the outer solar disk, some delivered later. The disk explains the body. The atmosphere arrives with questions still attached. The disk's final act is dispersal. It does not happen all at once. The process is gradual, the gas slowly thinning over the same timescales that the solar disk surrounding the whole young sun is thinning, both driven by the radiation pressure and stellar wind of the star that anchors the whole system. The outer edge of the circumplanetary disk thins first, the gas there too weakly held to resist the solar wind, then the middle regions, then, last and most slowly, the dense inner zone near the planet, where gravity holds the gas longest. Through all of this, the moons continue to orbit. They are large enough that the thinning gas affects them less and less as the density drops. Their inward drift slows. The force that had been carrying them toward the planet weakens and fades and eventually disappears. In those last million years of the disk, the surviving moons settle. Their orbits, no longer disturbed by the gas, stabilize under the influence of gravity alone. Their own gravity, the planet's gravity, the mutual pulls between neighboring moons. These pulls lock the inner 3 moons into a particular pattern. For every orbit completed by the outermost of the inner 3, the middle completes exactly 2, and the innermost completes exactly 4. 1 orbit, 2 orbits, 4 orbits, ticking in perfect ratio, each moon tugging gently on the others at regular intervals, the system settling into a rhythm that will hold for billions of years. This is an orbital resonance, a gravitational conversation conducted in repeating intervals, and once the disk is gone and there is no gas to disturb it, the resonance can maintain itself indefinitely. The heat from that resonance flows. When a moon in resonance passes close to its neighbor on a regular schedule, the tidal force from the neighbor flexes the moon's interior slightly. The flexing generates heat. For the innermost moon, the flexing is most intense. It passes close to both its neighbor and the planet itself, with each orbit, and the tidal forces from both combine to work its interior like a repeated gentle compression. The heat generated by this flexing is enough to keep the moon's interior partially molten, even though the moon is small and would long since have cooled to a solid state without the continuing input. The moon does not cool, it remains hot inside, and a world with a hot interior expresses that heat the way hot worlds do, through its surface. Volcanoes, not dozens of volcanoes, but hundreds, the most volcanically active body in the solar system, its surface covered in sulfurous yellows and oranges and reds and whites, the colors of sulfur and its compounds at various temperatures, the landscape repaved constantly by eruptions that keep it younger looking than any other solid surface in the solar system. All of this from the arithmetic of orbital ratios. All of this because the geometry of the disk and the timing of the last generation's survival placed these four worlds in exactly the spacing that produces this resonance. From the outside, the four moons of Jupiter, seen against the planet's banded face, express something of the process that made them each one different from the others, not because different forces acted on each, but because the same forces acted on each at different distances. The innermost is dry and volcanic. The next two carry water ice in their interiors and may harbor liquid water beneath their frozen surfaces, kept liquid by the same tidal heating that keeps their neighbor hot, only gentler, only enough to melt ice rather than rock. The outermost is cold and perhaps only partly sorted, a world that formed too far from the heat and too late in the disk's life to fully differentiate. Its rock and ice still mixed in proportions that speak of the cold, outer region of the disk where it gathered itself together from what was there. The pattern visible among them is the same pattern written at larger scale across the whole solar system, an inner region made of dense, warm material, an outer region made of light, cold material. The composition of each world a record of the temperature at which it formed. The temperature a record of the distance from the heat at the center of the disk. The solar system and the moon system are the same shape at different sizes, the same physics operating over the same gradients, producing recognizable results at every scale. There is a stillness to understanding this. The moons did not choose their compositions. The disk did not arrange the temperature gradient with any particular outcome in mind. The particles drifted and clumped and grew because the physics of rotating gas and solid material makes that happen wherever the conditions are met, in any disk, around any sufficiently massive body, in any corner of any galaxy, where a young star has laid down its rotating cloud of gas and dust and let it slowly settle. The moon systems of the outer solar system were not exceptions or special arrangements. They were the expected result of ordinary physics given time and material. Given enough time and material, they happened. The dust grains in a circumplanetary disk are each individually almost nothing. Each one is a particle too small to see without a lens, carrying no more mass than a few molecules of silicate or water ice. But in a disk, there are not a few of them. There are more than any number evokes easily, and each one, drifting on its slow trajectory through the gas, interacting with its neighbors, falling toward the midplane, is doing what physics requires of it, without any force beyond gravity and gas drag, and the geometry of a rotating disk. The vast result, a world 8,000 kilometers across, orbiting a gas giant in the cold outer solar system, its surface covered in ice, and its interior threaded perhaps by a global ocean of liquid water, comes from the accumulation of these interactions over millions of years. Grain falling onto grain, clump growing into clump, world slowly rounding from aggregate mass into sphere. The rounding matters. It is the mark of a world that has accumulated enough mass for its own gravity to draw it into a sphere, a threshold that separates a world from a pile of rubble, a threshold that once crossed changes everything about how the body behaves. A sphere has a center. A sphere has an interior. A sphere can hold heat in its deep layers long after its surface has begun to cool. And a sphere, warm enough inside, can differentiate, can let its denser components sink toward the center and its lighter components rise toward the surface, sorting itself by density over millions of years into the layered structure that planets have. The Galilean moons crossed this threshold. They became worlds, not boulders. They became worlds precisely because the disk had enough material and enough time to make them large enough. The disk's dispersal left them where they were. The gas thinned and lifted away on the solar wind, molecule by molecule, drawn off into the surrounding space, and lost. The disk that had driven them, supplied them, threatened them with inward migration, the disk that was the medium through which the whole process operated, was gone, and in its absence, the moons remained. 4 worlds in orbit around a vast planet, each one carrying in its composition the record of its distance from the center of a disk that no longer existed, in a solar system that was, for the first time, open to the light. There is a quality of completion in that moment, the disk gone, the moons present, the orbits stable, the resonance locked in. Everything that formed in the disk formed during a window that is now closed. The material that was available is the material that was used. The moons that survive are the moons that are there. Nothing will form from the disk again because the disk is no longer there. The open space that the disk filled is simply open space now, the sunlight reaching to the planet's surface without passing through the haze of drifting particles, the circumplanetary environment, clearing the way a morning fog clears when the air warms, gradually, then completely, and then gone. What remains behind is quiet. The orbits continue, the moons turn. The innermost one, kept volcanic by the resonance it inherited from the geometry of the disk, erupts quietly into its thin atmosphere, sulfurous plumes rising above a landscape that has been repaved so many times it carries no record of its earliest surface. The next world out, locked in its own gentle tidal rhythm, may hold in its deep interior a vast cold ocean pressed between a frozen outer shell and a rocky floor, the water kept liquid by heat that comes ultimately from the arithmetic of orbital spacing. The one beyond that, similar in size and composition, adds its layer of complexity, a magnetic field generated within it by some mechanism still not fully understood, a field that interacts with Jupiter's own enormous magnetosphere in a way that marks the moon's position even from a great distance. And the outermost of the 4 turns slowly in the cold, its ancient surface bearing the record of billions of years of impacts, a surface that has changed very little since the disk dispersed and left it behind. All 4 of them are there. All 4 of them have always been there, since the disk cleared, orbiting in the same ratios, maintaining the same gravitational conversation, carrying in their compositions the same record of the temperatures at which they formed. The disk that made them is the same kind of disk that makes moons everywhere in the universe that the conditions permit it. The gas accumulates around a massive planet. The solid particles settle toward the midplane. The streaming instability concentrates the material into clumps. The clumps collapse and grow. The moons spiral and survive or spiral and are lost, and the ones that remain when the gas finally goes are the ones that make the family. In the quiet, after the disk, the moons simply orbit. The planet they circle is vast and turbulent and banded in great storms that each dwarf the entire inner solar system's rocky worlds. The moons pass through the planet's shadow and emerge into the sunlight again. They pass across each other's view from the planet's perspective, one small disk transiting another, each world briefly visible against the clouds of its neighbor before the orbital geometry moves them apart again. The resonance ticks in its regular intervals. 1 orbit, 2 orbits, 4 orbits, the gravitational conversation ongoing, unhurried, older than any life that has ever looked up at a night sky and tried to count the points of light. Dust grains drifting in a disk, growing slowly into worlds through nothing more than the patient accumulation of ordinary forces, settling over millions of years into orbits that will hold for billions more. The disk makes what it makes from what it has. It wastes nothing and plans nothing and produces, from the simplest of ingredients, gas, dust, gravity, and time, a family of worlds as different from each other as cold is from heat, as ice is from stone, as the outer dark is from the warmth of the inner disk, each one a record of where in the disk it gathered itself together, each one carrying in its composition the precise memory of a temperature, a distance, a moment when the material was available and the conditions were right, and the grain fell onto grain, and the world slowly, over millions of years, became. The gas blew away, the sunlight came through, the moons turned in their finished orbits, silent and separate and whole, each one a different answer to the same question the disk had been asking since the first particle settled toward the midplane, and the first density clump thickened in the streaming gas, the question of what grows when the conditions are given and the time is long enough and the physics is allowed to follow where it leads. The answer, in this place, at this particular planet, in this particular disk, 4 worlds, each one different, each one carrying its record, each one turning still. In the beginning, before any planet had finished forming, the solar nebula spread across space in a vast, slowly turning disk of gas and dust. Warm near the center, where the young sun burned through the haze, and cold increasingly, utterly cold, toward the outer edge, where the light arrived already weakened from the long crossing and could not warm anything it touched. The disk did not have sharp boundaries. It thinned as it extended outward, the gas becoming more rarefied with every million kilometers, until at some great distance it simply dissolved into the emptiness of interstellar space, leaving no clear line where the solar system ended and the void began. Within that disk, the first dust grains moved in slow orbits, each one drifting on the breath of the gas around it, each one carrying the chemical record of the cloud collapse that had made the sun itself. Near the center of the disk, where the temperature was still high enough to keep water in vapor form, the grains were made of silicate and metal, small, dark, warm. Farther out, at a distance of roughly 2.5 to 3 astronomical units from the young sun, something changed. The temperature dropped below the point where water vapor could remain a gas. On the surfaces of dust grains at that distance, the first crystals of water ice were just beginning to form, not dramatically, not in any visible event, just a quiet deposition of ice onto grain surfaces that had been dry before, a coating, a thin layer, barely there, but enough to change everything. That boundary, where ice first became stable, would come to be called the frost line or the snow line, and the worlds that formed on either side of it would be as different from one another as stone is from water. Inside the frost line, the solid material available to build planets was limited. Only silicate rock and metal could survive in the heat so close to the sun, dense, dry, slow to accumulate. Outside the frost line, ice could contribute its mass to growing bodies, and the solid inventory of the disk increased rapidly. Where there was more solid material, larger cores could grow. Larger cores accumulated more quickly, and in the cold outer reaches of the disk where gases like hydrogen and helium had not yet been blown away, those large cores could begin pulling in gas, first slowly, then faster, in a runaway that gathered mass at rates the inner planets could never match. The giant planets grew outside the frost line because the frost line gave them the mass to start, and the gas gave them the mass to finish. In that cold outer zone, where the sun was a brilliant point among other points, and the light it cast barely warmed anything, planetesimals made of ice and rock were assembling from the same streaming instabilities and gravity-driven collapses that were building rocky bodies closer in. They were different bodies, though, lighter in composition, rich with the water and carbon compounds that the inner disk had never held in solid form. Their surfaces, if they had surfaces yet, were pale, white, and faintly bluish from the ice, dark in patches where organic compounds had gathered from the passing chemistry of the nebular gas. They moved slowly at those distances, following long orbital paths measured in years and decades rather than the months that inner planets would one day require. The disk was not a static place. Gas moved. Particles dragged on gas and lost orbital energy, drifting inward. Local overdensities grew denser through feedback that the physics of the disk made inevitable. A streaming instability in which particle concentrations and gas drag reinforced each other until material collapsed under its own gravity, producing the first real planetesimals, the first self-gravitating objects in a disk that had been until then nothing but a diffuse and slowly settling cloud. In the outer disk, these early bodies were icy. In the inner disk, they were rocky. In between them, at a position that would later correspond roughly to the outer reaches of the asteroid belt, the two populations met at the frost line and mixed in proportions that would take billions of years to sort out. Jupiter formed first among the giants because the outer disk at its distance was richest in solid material and its core could grow the fastest. That core, rocky and icy, several times the mass of Earth, accumulated rapidly, and once it reached a threshold, the gas of the surrounding disk began to fall inward toward it. The gas and fall fed on itself, and what had been a rocky core became a world of roiling atmosphere, growing without pause until the disk's gas ran out, or the planet's own gravity cleared a gap around its orbit. The disk that remained close to Jupiter, inside its orbital gap, would eventually supply material for the moons that formed in orbit around it, a circumplanetary disk, smaller and shorter lived than the solar disk itself, but governed by the same physics. Farther out, where Saturn formed later and grew more slowly, another circumplanetary disk would take shape around another giant world, and from it, another family of moons would grow. But before those moons finished forming, Jupiter moved. The solar nebula was still present, and a planet embedded in a gas disk does not simply sit still while the gas flows around it. Gravitational interactions between Jupiter and the gas on either side of its orbital gap produced a net force, and that force was inward. Jupiter began to migrate toward the sun, slowly by the standards of human time, but quickly by the standards of planetary formation. It moved through the region where the inner solar system's solid material was accumulating, scattering planetesimals and clearing the disk as it passed. The best current picture of this episode, still debated, still refined, is that Jupiter traveled inward to roughly 1.5 times Earth's eventual orbital distance before a different gravitational pull reversed its motion. Saturn, forming later and more slowly in the outer disk, eventually grew massive enough to lock into a gravitational resonance with Jupiter, a condition in which the two planets' orbital periods became related by a simple whole number ratio. That resonance pulled Jupiter back outward, reversing the inward migration and carrying both planets to something close to their current positions. The reversal happened on a timescale that was long by any ordinary measure, but brief by the measure of planetary formation, and it left behind a disk of solid material in the inner solar system that had been stirred, scattered, and truncated. The inner disk had less mass than it might otherwise have had, because Jupiter's passage had scattered much of it. And the planet that would eventually form at the position now occupied by Mars would grow to only a fraction of Earth's mass, because the material that might have built it larger had been disturbed before Mars could claim it. All of this, the frost line, the growth of giant planets, the inward and outward migration of Jupiter, happened within the first few million years after the Sun's formation, while the gas disk was still present. The gas was the medium through which migration happened, the medium through which circumplanetary disks were supplied, and the medium that connected the Sun to everything orbiting it in a single gravitational and hydrodynamic system. Without gas, migration stopped. Without gas, circumplanetary disks could no longer be replenished from outside, and gas disks around young stars do not last. Stellar radiation, stellar winds, and the gravitational stirring of the planets themselves all work to thin the disk and eventually disperse it, typically within 1 to 10 million years after the star's formation. 10 million years is a short window, measured against the age of the solar system, and within that window, the basic architecture of the planetary system had to be decided. Whatever had not finished forming when the gas cleared would finish forming without it, or not at all. The early moon was forming during some of this same broad period, accreting from the debris left by the giant impact in a disk that circled the young Earth. But the moon's formation was far faster than the Galilean moon's slow growth, finished in thousands or hundreds of thousands of years, not millions, and it was complete before the gas disk dispersed. The young lunar body settled into its early orbit in an outer solar system that was still assembling its giant planets, still moving gas from place to place, still producing the conditions that would eventually lead to the next great disruption. That disruption came later, long after the gas disk was gone, long after the giant planets had settled into orbits that seemed, from their surface, permanent. The outer solar system held a dynamical instability in waiting. Jupiter and Saturn were not yet in their current orbital relationship, and beyond them, the disk of leftover planetesimals, the building blocks that had never been incorporated into any planet, extended outward in a broad and slowly stirred band. Uranus and Neptune were there too, farther in than they would eventually end up, still embedded in the dense outer disk, and the gravitational architecture of the 4 giant planets was different from what it is today. It would not remain different indefinitely. Given time, and time was what the solar system had in a measurable supply, the slow accumulation of gravitational perturbations would push one or another pair of planets toward a resonance they could not hold. At some point, roughly 4 billion years ago, in a window that may have lasted as long as 300 million years after the planets formed, Jupiter and Saturn drifted into a condition near the 1 to 2 mean motion resonance, a configuration where Saturn completed one orbit for every two of Jupiter's. Resonances between planets amplify gravitational perturbations rather than damping them, and once the two largest planets in the solar system began trading momentum at resonant frequencies, the effect on the outer solar system was rapid and profound. Uranus and Neptune were scattered outward into the planetesimal disk. Pluto and thousands of other icy bodies were thrown into highly eccentric orbits, some falling inward toward the sun, others flung entirely out of the solar system into the dark between the stars. A large fraction of the bodies that fell inward ended up crossing the orbits of the inner planets. This produced a period of intense bombardment on all the rocky inner bodies, the early Earth, Mars, Venus, and the Moon. The Moon, lacking any atmosphere or geological processes to erase the record, still carries that history on its surface. Its great impact basins, Mare Imbrium, Mare Serenitatis, the Orientale Basin, are the scars left by impactors many tens of kilometers across, arriving in a wave of collisions that reshaped the lunar surface in a geologically brief period. Looking at those basins from the Moon's surface, the horizon would have been a landscape of overlapping circular walls and central peaks, each ring of mountains the frozen echo of an impact that had struck decades or centuries before. The sky above, periodically lit by the bright trails of new arrivals crossing from the outer solar system into the inner. The floor of a newly formed impact basin would have been a lake of slowly cooling melt rock, dark at the edges where it had already solidified, and still orange at the center where the heat of the impact had not yet escaped. In time, years for small impacts, many thousands of years for the largest, even those central pools would solidify, and the basin would become a flat plain of dark basalt surrounded by its ring of walls and rayed ejecta, exactly as the Maria look today. The record of that distant bombardment is still there, fixed in the lunar surface, because nothing has come to erase it. The Moon has no wind, no rain, no plate tectonics to remix its crust. The craters sit where they formed, waiting in stillness through the remaining 4 billion years. The bombardment that produced those basins was not caused only by the outer solar system's disruption. Part of the bombardment may have come from material already orbiting in the inner asteroid belt, perturbed by mean motion resonances with Jupiter. Part may have been the tail end of the formation process, leftover planetesimals that had not yet been swept up. The picture is not settled, and the proportions of different sources remain an open question, one that the cold, dark floors of the lunar highland craters do not yet answer clearly enough for certainty. What is clear is that the early inner solar system experienced a period of elevated bombardment, and that the timing and cause of that period are connected to the orbital dynamics of the giant planets in ways that took centuries of slow detective work to begin to untangle. The question of how water reached the early Earth is woven into the same picture of planetary migration, bombardment, and the compositional gradient that the frost line produced. The early Earth formed inside the frost line from dry silicate material. Whatever water it retained from its formation was likely lost during the giant impact, or at least severely depleted. The oceans that cover most of the Earth's surface today arrived later, delivered by something. The best current understanding is that much of that water came from carbonaceous chondrite meteorites, a class of dark, fragile, primitive rocks that formed in the outer asteroid belt, beyond the frost line's inner boundary, where they could retain water in their mineral structure. Their hydrogen isotope ratios match Earth's oceans closely enough to make them the most plausible primary source, though the picture is not perfectly clean, and other contributors likely played a role. A carbonaceous chondrite is an ancient object. It predates the Earth. Some of its material predates the Sun, carried over from the molecular cloud that the solar system collapsed from billions of years before any planet existed. That material, the dust, the organics, the water bound into clay minerals, made the crossing from the outer belt to the inner solar system on orbits disturbed by Jupiter's gravity, or by the gravitational shuffling that came with Jupiter's migration and the later dynamical instability. It arrived at the early Earth as part of the same general reign of impactors that was simultaneously carving the lunar basins, unremarkable in size, fragile, dark, breaking apart on entry into the atmosphere, or crumbling on the ground, releasing the water from its mineral bonds into the forming oceans. Grain by grain, impact by impact, over hundreds of millions of years. The moon received water too, though far less of it. The moon's lower gravity made it harder to hold volatiles delivered by impact, and most of what struck it was lost to space. What remained gathered in the coldest places, the floors of craters at the lunar poles that have never received direct sunlight, regions where the geometry of the moon's axis keeps permanent shadow in the basin floors. In those places, temperatures can fall to levels that are among the lowest of any stable natural environment in the inner solar system, so cold that water molecules that drifted there, whether from ancient comets or from volcanic outgassing, or from the solar wind's interaction with lunar surface minerals, have stayed frozen, undisturbed, for very long periods. The existence of that ice confirmed when an impactor was deliberately sent into one of those shadowed craters, and the resulting plume was analyzed from orbit, tells a story about the slow accumulation of volatiles across deep time in places where almost nothing else happens. The gas disk that made all of this possible, that fed the giant planets, that connected them to their circumplanetary disks, that provided the medium through which Jupiter migrated inward and was pulled back out, was itself temporary. Stars disperse their protoplanetary disks on timescales of a few million years, sometimes longer but rarely more than 10. The process is not violent. Stellar ultraviolet radiation ionizes the gas at the disk's outer edge, allowing it to escape on the stellar wind. The inner disk drains onto the growing planet, starved of resupply as the outer disk thins. The midplane, which had been opaque enough to block direct starlight from reaching the solid material inside it, becomes transparent as the gas thins and the dust settles or is swept away. The disk dissolves from outside and from inside at once, and what remains when it is gone is a set of solid bodies in stable orbits, or in orbits that will become stable over a much longer subsequent period of dynamical settling. When the disk cleared, the solar system's architecture was exposed to open space for the first time. The planets were not yet in exactly the positions they hold today. The later dynamical instability would move the giants, but the broad outlines were fixed. The inner solar system had its rocky planets, each one a world built from dry silicate and metal, each one carrying the isotopic record of the particular part of the disk it had formed from. The outer solar system had its giants, wrapped in deep atmospheres of hydrogen and helium, their gravity already shaping the disk of icy planetesimals that would persist beyond them as the Kuiper belt. Between the inner and outer solar system, the asteroid belt held the remnants of material that had never coalesced into a planet, partly because Jupiter's gravity had stirred the region too energetically for accretion to proceed, partly because the Grand Tax passage had depleted the region of much of the mass that might have built a Mars-sized body there. The silence that followed the disk's dispersal was not an absolute silence. Impacts continued. Orbits continued to be nudged by mutual gravity. The moon continued to recede from Earth as tidal forces transferred angular momentum outward from Earth's spinning interior to the lunar orbit. The continents of the early Earth had not yet formed in the configuration they would eventually assume. The atmosphere was different, thinner, younger, still being shaped by outgassing and by the continued delivery of volatiles from the outer belt. Life had not yet appeared, or if it had not yet left a record that survives in the rocks we can examine today. But the framework within which all of this would happen, the distances, the masses, the orbital periods, the composition gradients set by the frost line, was set. The frost line had determined where ice was stable and where it was not, and from that single boundary, the architecture of the entire solar system had cascaded. The inner planets were dry and rocky because they formed inside it. The outer planets were vast and gas-rich because they formed outside it, where solid material was abundant enough to build the cores that gravity then wrapped in gas. The moons that formed around those outer planets carried compositions that reflected the temperature gradients of their circumplanetary disks, which in turn reflected the temperature gradients of the solar disk that had fed them, and the water in the Earth's oceans had traveled from beyond the frost line, carried by impactors whose orbits had been perturbed inward by the gravitational shuffling of a solar system still in motion. All of that, the frost line, the migration of Jupiter, the great bombardment, the delivery of water, happened in a window of time that, measured against the age of the universe, is not long. The solar system is roughly 4.5 billion years old. The universe is roughly 3 times that age. The disk that built the solar system had dispersed before the solar system was 10 million years old, a fraction of a percent of its total lifetime. The dynamical instability that caused the late bombardment may have occurred several 100 million years after the disk cleared. The delivery of most of Earth's water was complete within the first billion years. From the perspective of the solar system's full lifetime, all of this was early, a brief, violent, defining period of formation that left the system in the arrangement it still holds today, still orbiting the same star, still largely in the same relative configuration, changed mainly by the slow recession of moons, the occasional perturbation of a comet from the outer reservoir, and the almost imperceptible drift of planetary orbits over timescales too long to have been directly observed. The 4 giant planets sit in their current orbits, and their gravity continues to shape the trajectories of smaller bodies as it always has. Jupiter's immense gravity captures some of the objects that fall inward from the Kuiper belt, bending their paths into shorter period orbits closer to the Sun, where they become the comets visible from Earth as bright streaks of sublimating ice. Others are accelerated by Jupiter's gravity and flung out of the solar system entirely, joining the long dark migration of interstellar objects that pass through other stellar systems as visitors, never slowing long enough to be captured. The solar system is not a static arrangement. It is a slowly stirring, continuously gravitationally active system, and the same forces that built the planets in the first place are still at work on timescales too slow to register as change within any human life. The boundary that the frost line represents no longer exists in the same form. The disk is gone. The temperature gradient that made ice stable at 2.5 to 3 astronomical units was a property of the disk, not of the solar system as it exists today. A dust grain at that distance now receives enough sunlight that water ice on its surface would sublimate. There is no disk gas to keep the surroundings cold, and no thick midplane to shield from stellar radiation. The frost line was a temporary feature of a temporary structure, and the worlds it helped create are the permanent record it left behind. They are the inscription of a condition that no longer exists, written in the compositions and positions of planets and moons that will orbit this star for billions of years to come. A warm, slowly dispersing zone of gas and dust, stretching from the young sun outward for hundreds of astronomical units, populated with drifting grains and slowly aggregating clumps of ice and rock, alive with the quiet physics of streaming instabilities and gravity. That is what existed once. The solar nebula had no edges sharp enough to see. It had no sudden beginning or decisive end. It assembled slowly from the collapse of a molecular cloud, built up through the free fall of material toward the forming star at its center, and then slowly, over millions of years, was consumed or dispersed by the same stellar energy it had helped to create. It filled the space where the planets now orbit, and when it was gone, the planets were there in its place. The disk thinned, the gas at the outer edge, heated by the young sun's ultraviolet light, expanded and drifted outward, escaping the sun's gravity in a slow, invisible outflow. The inner disk drained onto the forming planets or onto the sun itself, each in fall of gas, giving up its orbital energy as heat that radiated away into space. The midplane, where the solid material had been densest, was swept cleaner and cleaner as the gas that had suspended fine dust particles weakened and the particles settled or coagulated into larger bodies, no longer so easily moved. And somewhere in that process, at a moment that left no particular monument and produced no visible flash, the disk reached a threshold of thinness at which it could no longer be distinguished from the interplanetary medium that would persist in the planet's final solar system. Sunlight crossed the cleared space directly for the first time, reaching the inner planets without passing through the haze of the disk. The young sun stood exposed in a sky that was still dense with the debris of formation, asteroids, comets, scattered planetesimals, but open enough that a world's surface could have seen stars clearly, for the first time, through a sky that was no longer one continuous cloud of forming matter. The architecture of the solar system had settled into something recognizable. The planets continued in their orbits. The moons turned around their planets. The ice and the shadowed craters of the moon settled into permanent cold stillness. The water in the forming oceans of the early Earth moved in currents driven by heat and the moon's tidal pull. The sun burned steadily at the center of all of it, its nuclear fusion converting hydrogen to helium in a process that would continue for another 5 billion years, warming the same zone it had always warmed, holding the planets in the same gravitational arrangement that the collapse of the nebula had originally produced. Everything that had happened in the disk, the growth of planetesimals, the formation of giant planets, the migration of Jupiter, the delivery of water, had happened within that zone, had shaped what that zone contained, and had finished long before the arrangement it produced began to feel old. The vast, slowly turning disk was gone. In the stillness it left behind, the solar system continued, patient and dark and precisely arranged, the dust of its origin still drifting in small quantities between the planets, still catching the sun's light in the faint glow that a clear dark sky will sometimes show along the plane of the ecliptic, a ghostly remnant of the disk that made everything, still present in trace, still moving in the same slow direction, a last faint residue of the cloud that once filled all of this space, and that quietly, over millions of unhurried years, became the worlds. The moon in its earliest solid form was a world on fire with its own making, not the sharp fire of burning, but the deep, slow fire of a planet still holding the heat of every collision that built it, a warmth so vast and so even that it had no center, no edge, no direction to escape toward except outward into the cold of space, one slow degree at a time. The surface, if it could be called that, was not yet solid in any familiar sense. It moved, it breathed, in long, slow exhalations of gas rising through viscous rock, become darkened in places where a thin crust tried to form, and then cracked, and the orange below came through again, slow and patient as a tide, unwilling yet to be contained. This was the lunar magma ocean, a world entirely molten, or nearly so, from its outermost surface down through kilometers of liquid rock to whatever lay below, a body still in the process of deciding what it was going to be. The heat did not come from burning and would not last forever. It was the stored memory of accumulation of 10,000 smaller bodies falling together, each collision adding its kinetic energy to the whole, converting motion into warmth across the span of a few tens of thousands of years. And now the accumulation had stopped, and the warmth was working its way out. Slowly, over millions of years, the moon would cool from the outside in, and what it became in the cooling would depend entirely on the order in which its minerals found their solid form. Cooling is not simple. In a world made of rock, different minerals solidify at different temperatures, and the order of that solidification determines which materials end up where. In the lunar magma ocean, the minerals that crystallized first were the dense ones, olivine, pyroxene, heavy silicates that sank through the remaining liquid as soon as they formed, settling toward the interior under the gentle pull of the moon's own gravity. The liquid above grew lighter as the dense minerals left it, and then, later, when the temperature had dropped far enough, a different mineral began to crystallize, plagioclase feldspar, pale and light, less dense than the remaining liquid, unable to sink. It rose instead. It floated. Slowly, in thin sheets and growing rafts, it accumulated at the surface, crowding together, thickening, until it formed a crust across the entire young moon, pale and continuous, a global skin of mineral foam. That pale crust is still visible today in the lunar highlands, the oldest terrain on the moon, the direct record of a planet sorting itself by weight 4.5 billion years ago. The heat beneath the crust continued outward for a long time. The magma ocean did not solidify all at once, and the moon passed through a long middle period, perhaps tens of millions of years, in which the interior was still partly liquid, while the surface above had already hardened into something that could, from a distance, have been mistaken for solid ground. Beneath that ground, the slow process of differentiation continued, the heavy settling downward, the light rising, the moon arranging its interior into concentric shells, the way any large liquid body does, when gravity has time enough to work through it. At the very center, iron and heavier elements gathered, pressing inward, compacting. The small iron core of the moon began, quietly to form. That core is still there. It is not large, roughly 300 to 400 kilometers across, a modest sphere of iron-rich material at the center of a world 1,600 kilometers in radius. On Earth, the iron core is vast, comprising more than 30% of the planet's total mass, a dynamo that still spins and generates the magnetic field that wraps the planet in a protective envelope. The moon's core is much smaller in proportion, and it is quiet today. No dynamo runs inside it. No magnetic field rises from the moon's surface and reaches outward into space. The moon now moves through the solar system magnetically still, a world without a shield, but it was not always so. The rocks brought back from the lunar surface by the Apollo missions carried within their crystal structures the faint signatures of magnetic fields that no longer exist, fields that were present when the rocks first solidified, imprinted in them like the memory of a wind that has long since stopped blowing. Those signatures suggest that the moon sustained an active magnetic field for hundreds of millions of years, beginning around 4.2 billion years ago and fading away somewhere around 3.5 billion years ago. How a body as small as the moon could have maintained a functioning dynamo for that long is a question that has not yet been answered with confidence. The core is too small, under the standard models, to have generated a field strong enough to match what the ancient rocks record. Something else may have been at work, a different source of the energy needed to keep the liquid iron of the outer core in motion. Perhaps the gradual crystallization of the inner core itself released enough heat. Perhaps the slow stirring of the mantle above provided a forcing that kept the core churning. No one knows yet, and the small silent core at the moon's center holds its answer in a language that has not been fully translated. The moon's crust, once formed, became the record of everything that followed. The early solar system was not a quiet place in those first hundreds of millions of years. Large objects moved through it in numbers that have since dramatically declined, planetesimals and protoplanets, and fragments of all sizes, crossing orbits, encountering one another, occasionally striking. The moon, with no atmosphere and no weather and no geological recycling of the kind that erases Earth's impact scars, received each of those collisions and kept them. The craters that mark the lunar surface today are not a random sample of time. They are skewed toward the ancient because the rate of impacts was highest early and has fallen steadily since. The oldest large impacts created the Great Basins, circular wounds hundreds of kilometers across, where the crust was punched through and the rock beneath was briefly melted and thrown outward in rings of debris. Those basins are still there, still round, still readable as the record of what the early solar system threw at every surface it could find. The near side of the moon, the face that always looks toward Earth, is covered in dark flat plains called maria, singular mare, a Latin word for sea. They are not seas. They are ancient lava flows that flooded the great impact basins from below, somewhere between 3 and 3.5 billion years ago, long after the basins themselves were formed. Beneath the surface of the near side, heat from the moon's still cooling interior melted rock in the mantle and drove it upward through cracks in the thinned crust, spreading across the basin floors in dark, slow floods that took millions of years to accumulate their full depth. The dark color is the color of basalt, the same volcanic rock that makes up the floors of Earth's ocean basins, iron-rich, dense, and fine-grained from cooling quickly at the surface. When the volcanism finally ended, the lava plains solidified and were still, and they have been still, largely, ever since. The Maria carry fewer craters than the highlands that surround them because they are younger by almost 1 billion years, and the bombardment rate had already fallen substantially by the time the lava cooled. The largest craters on the Maria are recent visitors by geological standards, their sharp rims still fresh, their floors not yet blurred by billions of years of smaller impacts. The far side of the moon is different in a way that still resists a fully satisfying explanation. The far side has almost no Maria. Its crust is pale and ancient and heavily cratered, more like the oldest highland terrain of the near side than like the dark volcanic plains that fill so much of the hemisphere facing Earth. The far side crust is also thicker, averaging around 60 kilometers, compared to roughly 30 kilometers on the near side. This asymmetry is one of the most persistent puzzles in lunar science, because the moon formed as a single body from a single disk of material, and there is no obvious reason why the two hemispheres should have ended up so different. Several explanations have been proposed. One suggests that the far side's thicker crust made it harder for the mantle heat to break through, suppressing volcanism there, while it proceeded freely on the near side. Another invokes a very different kind of event, the possibility that early in lunar history, before the crust had fully solidified, a second smaller body collided gently with the far side and piled its material there, thickening the crust by addition rather than by chemical differentiation. The evidence is suggestive, not conclusive. The asymmetry remains, and it remains an open question, the kind of question that can be asked loudly by looking at the moon's two faces and asked more quietly by studying the returned rock samples, and still remain, for now, without a clean answer on either side. The far side of the moon was unseen by human eyes until the year 1959, when a Soviet spacecraft called Luna 3 swung around the moon's trailing hemisphere and photographed it for the first time. The images were rough and indistinct by later standards, but they showed what was there. Craters on craters on craters, pale and continuous, no dark seas, a landscape that contradicted the assumption that the two hemispheres must be similar. That assumption dissolved quietly with those first pictures, and what replaced it was not an answer, but a question that is still being worked through more than 6 decades later. Beneath the crust, below the deep mantle, below the boundary where solid rock gives way to something slightly less rigid, the small iron core sits. Surrounding it is a region that may be partially molten, a zone where iron sulfides and other low melting point materials have not fully solidified, a boundary layer between the crystalline core and the silicate mantle that speaks to the long thermal history of the body's interior. Seismometers placed on the lunar surface by the Apollo missions recorded thousands of small moonquakes during their years of operation, and the data from those instruments, reanalyzed by later researchers with better tools than were available at the time of the original missions, has provided the best current picture of the moon's interior structure. The signals of deep moonquakes, mostly occurring in clusters at depths of several hundred kilometers, pass through the moon along paths that reveal what the interior is made of, the way the sound of a knock tells something about what is inside a wall. From those paths, the core's approximate size was inferred. From the slight damping of seismic waves near the core mantle boundary, the partial melt was suggested. The picture is incomplete. 4 seismometers is not many for a body the size of the moon, and a more complete picture awaits future instruments, placed at more locations, recording over longer baselines of time. The moon is not where it was. From the time the moon formed in the debris disk close to the young Earth, gravity and time have been slowly moving it outward. The mechanism is tidal friction. Earth's gravity raises a tidal bulge on the moon, locking its rotation so that it always presents the same face. The moon's gravity raises a tidal bulge in Earth's oceans and solid rock, but Earth rotates faster than the moon orbits, so this bulge is dragged slightly ahead of the line, directly beneath the moon. The bulge pulls the moon forward, adding a little energy to its orbit, nudging it to a slightly wider path. The moon drifts outward. Earth's rotation slows, a tiny fraction of a second per century, the energy of the planet's spin bleeding away into the widening gap between the two bodies. The recession is not fast, 3.8 centimeters per year, a rate at which a human fingernail might grow across a single month. But across geological time, 3.8 centimeters per year is not small. 4 billion years of that rate, even accounting for the fact that it has varied as the configuration of Earth's oceans has changed, amounts to a very large distance. The moon today orbits at a mean distance of 384,000 kilometers. Early in its history, it was much closer, perhaps 10 times closer, in the first years after its formation, a vast silver disk dominating the sky above the young Earth's surface, raising tides in the global ocean orders of magnitude stronger than the tides it raises now. The precise rate of recession is known because it has been measured directly in one of the quietest and most patient experiments ever conducted. In the years between 1969 and 1972, Apollo astronauts placed small arrays of corner cube reflectors on the lunar surface at several landing sites. Flat, prism-shaped mirrors, each one oriented so that any light striking it returns in exactly the direction it came from. From observatories on Earth, laser pulses are fired at those arrays. The light takes just over a second to reach the moon, a second for the reflectors to throw it back, and just over a second to return. The round-trip time, measured to the nanosecond, gives the distance to the reflector with extraordinary precision. Over decades of these measurements, the slow increase in the travel time has been tracked, not with clocks, but with the accumulating count of returning pulses, each one arriving a little later than the last series, encoding in that lateness the moon's patient, imperceptible drift. The reflectors are still there, in the lunar dust, at sites that have not been visited in more than 50 years. They are passive instruments, no power source, no electronics, nothing to maintain or to fail. A corner cube reflector works by geometry alone, and geometry does not decay. As long as there are lasers on Earth to fire at them, and telescopes to catch the returning light, they will continue measuring the moon's recession with the same precision they have delivered since the first successful return signal was recorded. The distance between the Earth and the moon, measured to within a centimeter, changes by 3.8 centimeters each year, and has changed in that quiet, regular way, while nations rose and fell, while the climate shifted, while the species on the planet's surface changed beyond recognition from what they were when the pulses first began. The moon moved, and the lasers tracked it, and the number grew. There is water on the moon, not in rivers, or pooled on the surface, or anywhere visible from Earth. The moon has no atmosphere to speak of, only the thinnest wisp of molecules that barely qualifies as one, and liquid water under those conditions would evaporate immediately into space. But in certain places near the lunar poles, water is present in a frozen form, locked into the soil of craters whose floors have not seen sunlight in billions of years. The moon's axial tilt is slight, just over 1.5 degrees compared to Earth's 23, and this means that the poles receive sunlight that grazes the surface at very low angles, never reaching down into the deeply shadowed interiors of craters that happen to sit near the poles. In those interiors, the temperature can fall to around minus 230 degrees Celsius, among the coldest stable temperatures anywhere in the solar system, colder than the surface of Pluto during much of its year. At those temperatures, water molecules that drift into the crater interior and settle to the floor do not sublimate back into space. They stay. They accumulate, molecule by molecule, over millions and billions of years, building up a thin layer of water ice mixed into the regolith, the fine dust of shattered rock that coats the lunar surface to considerable depth. The conformation of this water came from an experiment that was, in its way, deliberately destructive. In 2009, a spacecraft called L-Cross, a set of letters whose meaning matters less than what the craft did, was directed to impact the floor of Cabeus crater near the lunar south pole at high speed, kicking up a plume of material from the shadowed floor into sunlight, where its chemistry could be read by a following spacecraft. The plume rose, and in it were water molecules, detectable by the specific wavelengths of light they absorbed, a spectroscopic signature as distinct as a fingerprint. The water was there, not abundant, not a thick ice sheet, but a modest fraction of the excavated material, enough to confirm what orbital observations had suggested and what the physics of permanently shadowed craters had long predicted. Water existed on the moon, in the dark, in the cold, in places that had been undisturbed since before complex life appeared on Earth. Where that water came from is a question with several possible answers, and no clean way yet to choose among them. Some of it may have arrived with comets and asteroids that struck the moon across geological time, the same delivery process that brought much of Earth's water to the inner solar system. Some may have formed through solar wind chemistry, hydrogen ions from the sun, striking oxygen-bearing minerals in the lunar soil and combining to form water molecules one by one, a slow and steady production that has been running for billions of years. Some may have been released by volcanic outgassing in the moon's more geologically active past, water vapor rising from the interior and eventually freezing out in cold traps at the poles. All three sources are physically plausible. All three have some supporting evidence. The relative contribution of each remains, for now, an open proportion without a settled value. The water in those permanently shadowed craters has been there a very long time. The ice in the floor of Cabeus has not been disturbed since it formed. There is no wind to move it, no seasonal warming to melt and refreeze it, no geological process churning the material from below. It has simply sat in the dark and the cold, accumulating its thin layer of ancient ice, while on the planet below, the oceans formed and life appeared, and the first photosynthetic organisms began producing oxygen, and then multicellular life, and then everything that followed. The ice was there for all of it, undisturbed, in a cold that makes any cold on Earth seem modest by comparison, in a darkness that has not been broken in 4 billion years. To stand on the rim of Cabeus, which no person has done, and look down into it would be to look into a darkness with no bottom, at a floor invisible even to eyes fully dark adapted, a floor colder than almost anything else in the solar system, holding its ancient frozen record beneath a sky blazing with stars and a distant blue and white planet filling a significant arc of the horizon. That planet, seen from the moon's surface, does not rise or set from any fixed point on the near side. Earth sits in the same part of the sky, always. It swings slightly in a slow wobble driven by the eccentricity of the moon's orbit and its slight inclination, a motion called libration that allows Earth-based observers to see slightly more than half the moon's total surface over time, and that causes Earth, seen from the lunar surface, to trace a slow ellipse in the sky rather than a fixed point, but it never rises above the horizon if the observer is on the far side. It never sinks below the horizon if the observer is on the near side. It simply hangs there, waxing and waning through its phases exactly as the moon waxes and wanes for earthbound observers, and its light falls on the near side of the moon during the lunar night, the soft reflected glow called earthshine, bright enough in those quiet nights to cast faint shadows across the dust. The lunar surface where the dust lies is not like any dust familiar from Earth. It is called regolith, a word for the layer of fragmented and pulverized rock that blankets the moon to depths of several meters in most places and tens of meters in the oldest terrains. Billions of years of micrometeorite impacts have ground the surface rock into fine particles, and because there is no wind, No water, no freeze-thaw cycle. The regolith is not sorted or rounded the way Earth's soil or sand is. The grains are angular, glassy, sharp at the microscopic scale, each one a tiny fragment of rock shattered by an impact, often coated with glass fused from the heat of the impact that made it. Apollo astronauts who worked in the regolith found that it clung to everything, to suits, to equipment, to tools, because its sharp-edged particles interlocked with any surface they touched, a static and physical grip that no amount of brushing fully released. The dust carried the history of its own creation in its shape, in the glass beads mixed through it, in the solar wind gases absorbed into its surface over billions of years of exposure. The highlands stand above the Maria, pale and ancient, their surfaces so thoroughly cratered that new craters overlap old craters, and the original topography of the highland crust has been largely obliterated by the accumulated record of 4.5 billion years of bombardment. The impact rate was highest in the first half-billion years, and there is evidence that it spiked again during a period roughly 4 billion years ago, the late heavy bombardment, a time of elevated impact flux that left its mark on the moon as a series of large basins formed within a relatively compressed window of time. The cause of that spike is not fully settled. The most influential model connects it to a rearrangement of the outer solar system, the giant planets shifting their orbits through resonance interactions, scattering large numbers of smaller bodies into the inner solar system in a wave that lasted tens of millions of years. The moon's highlands bear the record of that wave in their basin count, and in the ages of the materials melted and reset by those impacts, ages that cluster conspicuously around 3.9 billion years when measured from rock samples returned by the Apollo missions. The moon that looks down on the dark side of Earth tonight is the same moon that recorded all of this, the same pale highlands, the same dark Maria, the same polar craters in their permanent cold, the same small silent core at its center. None of it is visible from the ground in the sense of being directly readable. A naked eye looking at the full moon sees the dark and light patches and can hold in mind, if it chooses, the story of what those patches are, the ancient anorthosite of the highlands, the later basaltic flows of the Maria, but cannot see the layered interior or the water at the pole, or the laser reflectors sitting in the dust at the landing sites, 3 small arrays of glass prisms that have been returning light to Earth for more than 50 years. The recession continues. 3.8 centimeters this year, 3.8 centimeters next year. The Earth's rotation slows by a small and measurable amount each century, the energy draining into the widening orbit. In the very far future, if the sun did not intervene, the process would eventually reach an end state, the Earth and Moon tidally locked to each other, both showing the same face to their partner, the length of the day on Earth equal to the month of the Moon, everything settled and still in a mutual gravitational embrace. But the sun will intervene long before that end state is reached, expanding as its hydrogen runs low, and engulfing the inner solar system in a transformation that makes the moon's gradual recession seem brief by comparison. The moon's recession is a process running now, quietly, measurably, in real time, carrying the Earth-Moon system along a trajectory that has been unfolding since the first weeks after the moon's formation, when it orbited close and raised its enormous tides in the young Earth's shallow, warm global ocean. The moon hangs tonight above the dark side of the planet, the way it has hung there every night for 4.5 billion years. Its near side faces down toward the sleeping surface below, toward the oceans and the continents and the weather systems moving across them, toward forests and mountains, and the thin lit lines of cities on the dark side of the Terminator